Okay, March 24, 2022. So, like I mentioned, you know, you have to know how to solve problems of circuits, resistors in series and resistors in parallel. So far, we have looked at problems with a single resistor and two resistors only. We did problems for two resistors in series and two resistors in parallel. But then you can have something far more complicated than that. You can have circuits that have resistors connections that are both in series and parallel. And I need you to practice that at home. Okay, so here you go. Two resistors, one resistor in a single circuit, two resistors in series, right? And these two resistors in series can be reduced to a resistor, to a circuit with a single resistor, equivalent resistance R12. Okay, so here you go. Here you go. Resistance, equivalent resistance, REQ. And then you can have resistors in parallel, right? Just like that. Current flowing coming from the main branch is stronger, and when it reaches this junction, it splits into branches. Okay? This circuit, just like I mentioned, can also be treated as a circuit that has a single resistance. That would be the equivalent resistance. And by the way, the current here would be the same as the current as the incoming current in this equivalent circuit. Here you go, like that. Can I do better than that? Take it, get rid of that. Okay, and we can have three resistors in series. Okay, we combine two of them and then combine all the three together. That's what we call the equivalent resistance, but I can call whatever I want. I can call R1, 2, 3, right? So here you go. We have three resistors in parallel. We can combine those two and the third one. Okay, and then you can have combinations like those ones that you are seeing. Circuits in series combined with circuits in parallel. Those two are in series and those two are also in parallel with respect to this one. So if you want to solve, for instance, for the current I, first I have to know what's going to be the equivalent resistance. The equivalent resistance is going to be R12, which is R1 plus 12, R2. And then we have these two resistors in parallel. Okay, here you go. That end up to be R123. The inverse of R123 is equal to the inverse of R12 plus the inverse of R3. Okay? So practice those circuits there at home so you understand exactly how those things work. We can even put capacitors there as well. So you can have a circuit with resistance and capacitance. Okay, we're going to see that later on, not now. And then there are circuits that we cannot classify neither as circuits resistors in series nor in parallel. That's the oddball here that you see right in here. This is a bridge circuit. It's very difficult to see if this thing is in series or in parallel. Actually, you cannot say whether it's in series or in parallel. Okay? This guy here is not in parallel with this one because I have this third resistor right in here. Okay? And this guy cannot be said to be in series with this one because we have this other resistor here. This is a bridge type of circuit. If instead we didn't have something like that, if instead we had something like that, then yeah, then we could say for sure that those two circuits are in series, those two circuits are in series, and their combination are in parallel with these other two, okay? But for this type of circuit here, we do not solve it using circuits in series and circuits in parallel. We use a different technique, a far more powerful technique. Okay, so let's write that down. Okay, most problems you see, most problems you will see are problems that involve resistors in series and parallel. However, there are some problems out there that you cannot identify any connection in series and parallel. For these cases, we must use a different technique to solve our problems. More on that later on. Okay, here we go. This one clearly is going to be two resistors in series and two resistors in series. Those two resistors in series will be parallel to those two resistors in series. How do I know they're in parallel? Because the potential difference between those two ends here is the same as the potential difference between those two ends here. This resistor is not in parallel with this one because this end is not connected to this other end. Okay? And here you go. Here's another type of circuit that you cannot easily solve using identifying your resistance in series and parallel. It's a circuit that has two batteries, two power sources, pumping in opposite direction. See that? This guy here, the positive of this one is facing the positive of this other one. So this one is pumping current from in the counterclockwise. This one is pumping current in the clockwise. Whichever has more energy, whichever has a higher voltage, is going to prevail in this type of circuit. For this type of circuit, you use a different technique to solve this problem. Okay, we use what we call the Kirchhoff loop laws that I'm going to introduce to you now. Kirchhoff loop law. For these type of problems and others, we use the so-called Kirchhoff loop law. Which is nothing more than two separate statements. One about the first one is a statement of conservation of energy in the circuit. And the other one a statement of conservation of electric charge in the circuit. Okay. Here you go. In this one here is the loop. We call it a loop. And this other one, we use what we call, let me see if I remember here. We have loops and we have intersections in a circuit. Let's go there. Direct current circuit, we go. Kirchhoff loop law. Nodes. We have loops and nodes. Okay, so loops, and here we call the nodes. This is a very powerful technique to solve almost any problem. We're going to start with this one. In this specific case, in this specific circuit, we do not have any nodes. Okay? We do not have any nodes. We have just one loop, a single loop. So in a way, it's one of the simplest problems that you're going to see out there. So what do? You start anywhere in the circuit and go through a loop. Here you go. Here's the loop. Let's say we start here with point A. First, what do? Here you go. First, you set a current. First you identify the loops and nodes of the circuit. Okay. Set the direction of the loop. Any direction you want. Any direction you want. Clockwise or counterclockwise. Either way is gonna work. There you go. What else? What else you do? Set the direction, of the current. Any direction would work as well. Would work as well. Okay, so those are the three important steps that you have to take. So going back to our simple problem, I set the direction of the loop as being clockwise. Doesn't matter if I did that counterclockwise, the problem still would work. Okay, so and I'm gonna here set the direction here, and I'm gonna do another step so to make it simpler for you all. Here you go. Then we identify some points along the circuit, and we label those points before and after the resistor. Here you go, A, B, C, D. Let's do that. You know, identify. Label some points along the circuit. In my case, I put A, B, C, D, Next, you set the direction of the current. Okay? Again, any direction you want. And then, you go ahead and you start accounting for the increase in potential energy and the decrease in potential energy. That's what you do. When you look at the loops, okay, direction of the current as well. When you, the next step is to get your equations for the loop. Can be more than one loop, right? For the loops. The loop equation, the equations for energy conservation, of energy conservation. Okay? Energy conservation means, or electric potential. Electric potential. After, Then you repeat that for the nodes. Then you repeat the above for the nodes. Solve your equations in terms of the unknowns. That's how you do it. Okay, so let's do an example right now with that circuit that you saw. Here you go. I'm going to go from point A to point B in my circuit. Here you go. Point A to point B. When you cross this battery, this power supply, I go from a region of lower electric potential, the negative one, to a region of higher electrical potential, plus. So I have to write that down, plus V. I'm gonna, did I put V1 there? Yep. Yeah, V1. Okay. So if your electron is moving from A to B, if your electric charge is moving from A to B, your electric charge is gaining potential energy. Is gaining potential energy. Now, however, when it passes through the resistor, remember what resistance does. This resistance just like electrical friction. So the electric charge is going to lose electric potential energy. Okay? So I can state that, here you go, is going to have a loss in electrical potential energy. I'm going to put like that. Oh, no, not. Let's put it this way. Here you go. Here you go. A loss of electrical potential across resistance, resistor 1. I'm going to erase this one because I don't need it. Okay, I have to go through the loop. Okay? We are moving the same direction of the current. Because we are moving the same direction of the current, we must have the negative sign in there. And now I'm going to move across the second battery. We're going to go from a region of higher potential to a region of lower potential. So your electric charge loses energy across that battery. I'm putting a negative here. We have to go another resistance. Okay, gonna lose electric potential. Gonna be a negative as well. It's gonna be R2. And then we finally go back to the initial point A, and we can state that since we're going back to the initial point A, we say that all that electric potential must be equal to 0. That's, despite having two batteries in there, two power sources in there, this is one of the simplest type of problem that you're going to see. Okay, and then later on you're going to see other problems that involve not just multiple loops, but also multiple nodes. Okay, here you go. Here's a problem that involves two nodes, but let's see. Well, there is more that we can do here. Let's not underestimate this problem, right? What you have to do here. So let's say calculate I, right? Calculate I in terms of V1, V2, and R1, R2, and R2. Okay, let's do this way. R1 and R2. So what do we do next? Okay, right in here and right in here, we apply Ohm's law. Okay, I set up the current. I do not know what was the value of the current, and I want to find out what's the value of this current. Okay, in terms of the other parameters. So we can go ahead and write I R1, I R2, I R2. Okay. And now what we have? Let me we have an equation, one equation. We know this guy. We know, I'm going to boldface what we know, okay? We know this guy, given. We know this guy. We know this guy. We know this guy. What we do not know is the I. One unknown and one equation. We can solve this equation. Let's combine the unknown with the known. Okay, so here we go. IR1, IR2. Go to the other side. Put it between parentheses. Okay, like that. Oops, don't need the negative, right? Take out the negative. And now I can solve my equation. Here you go. V1 minus V2, R1 plus R2. Okay, here you go. Now let's analyze this equation. I'm going to stop bold-facing thing here. This is a simple problem that helps you a lot understand how the whole thing works, okay? So here you go. If V1 greater than V2, right? I is going to be positive, right? According to this equation. According to this equation, comma, if V1 greater than V2, I is greater than 0. What does it mean, I being greater than 0? Okay, it means the following. It means that we chose the right direction for the current. That's what it means. Okay? We didn't know if the current was going to flow this way or if the current was going to flow the other way. But after, that's why I said it doesn't matter which direction you put the current, because if you get the direction correct, you're going to get a positive number. Okay? However, if V1 is less than V2, then what does it imply? It implies that the current is negative. Okay, so let's write that down. I is equal to greater than 0, and this means that you choose the current in the proper direction. However, if it's I less than 0, this means that the actual direction of the current is opposite to the one you chose. Okay, that's what it means. So if V1 is greater than V2, then the current is going to flow in this direction. But if it V2 greater than V1, then it means that the right direction of the current is going to be counterclockwise, okay? That's how you find out whether you choose the right direction or not. Now let's solve this one here. This one is a little bit more complicated because it has 2 nodes and 3 loops. 2 nodes and 3 loops. See, I have three loops. This outer loop, this inner loop, and this other inner loop. Okay, another example. Go. Here are the loops. I'm going to go little by little so I don't overwhelm you with too much stuff, right? I will start with this loop number 1. Go. I'm not gonna put the current yet. Oh, not what I want. Okay, loop number 1. Loop number 2. Gonna need more here. Go. Loop number 2. Loop number 3. Oh. And now we go for the currents, right? Step by step. Well, that's a node. That's one node. Okay. We can set up the currents in whatever direction you want. You know, you can say, let's say this. Yeah. You know, I'm setting up the current number 1 coming from this battery. You know, pumping current in this direction. We can say that the battery is pumping a current, the second battery is pumping a current in this direction. Because there is a junction right in here, this current 1 and 2 are going to somewhat combine and going to become I3. Okay, we can say that. Okay, so we go ahead. We also have another node here. Okay, we also have another node. See that we also have another node here, but the other node is not going to be necessary. Even though it's not going to be necessary, I'm going to put that for you. You know, this other node is going to basically be exactly the same thing in your opposite direction. Okay, like that. I1 going in this direction. If I2 is going in this direction, it means the I2. See, this branch here is the same, right? So they must have the same current. It's the same thing here in this branch. It has this single branch that has the same current. I'm going to shorten this guy so I can fit it properly there on the other side. Go. Yeah, we go. Now I can put, oh, not what I want. Here you go. Okay, and now because this current is the same branch as this other one here, we can No, that's not what I want. Size, save a picture, format shape. Here you go. Yeah, I too. Right. Okay. And then if I3 is in this direction, downwards right here at the spot, it means that we're going to have I3 going upwards here. Okay? Okay, so let's do that. Here you go. Let's do that again. Here you go. That's the circuit we have. Wait a minute. Ah, I put the current there. Yeah, I shouldn't be putting the current yet. We have this circuit. We identify the loops. Loop 1. Here you go. Yes. Oh, what did I do? Yeah, okay, good. Now I got it. Original circuit. I identify loop 1. I identify loop 2. I identify loop 3. Then we set up our current anywhere, any direction we want. Okay? I set up I1 in this direction, in this node. Here you go, I have one node here. And we must set up the currents in the other node as well. It happens that we don't need to set up a current in this node. There's a reason for that, okay? But I'm setting up anyway just so you can, you're going to see that there's no need for this type of circuit to set up the current in the other node. Here you go. Now we have it. Okay, here you go. And now, everything that you see here, 3 loops and 2 nodes, are a total of 5 mathematical equations. Okay? That's what we have. Actually, no, I'm going to be even better than that. It's actually 3 independent mathematical equations. Yeah, we can generate 5, yes, but out of those 5, only 3 are dependent. So 3 equations derived from the loop. There are only 2 independent equations. 2 equations derived from the nodes. There is only 1 independent equation. So what you see here is going to be exactly the same equation that you're going to find from here. Okay? And loops 1, 2, 3, similarly, one of those 3 loops will be an equation that's going to be a linear combination of the other 2 equations, okay? So that's a little secret that you have to know so you don't spend too much time solving these problems, okay? Here you go. In the displayed example, okay, we have, okay, another example, right? Another example. 3 loops and 2 nodes, okay? Each of the loops and nodes is a mathematical equation. strictly speaking, you are supposed to have 5 mathematical equations. Mathematical equations. Mathematical. Yeah. Mathematical. Is that right? Huh. I put something here. Yeah, here you go. Mathematical equations. However, in practice, you end up having 3 minus 1 and 2 minus 1 independent equations, or 3 independent equations. Okay? So if I given, so remember that if a given problem has m loops and n nodes, it means that you have to solve a system of m minus 1 plus n minus 1 independent equations. Okay? And it can get very complicated. Okay, think about that. 10 loops and, let's say, 7 nodes. Okay, it can become very, these problems, okay, these types of problems can become very complicated. Think about a circuit that has 10 loops and 7 nodes. Okay, think about the circuit that has 10 loops. What does it mean in terms of mathematical solution? What does it mean in terms of mathematical solution? Well, it means that we have to solve a total of 10 minus 1 equations related to the loop, plus 7 minus 1 equations related to the nodes. Something like that is equal to what? 15 equations. Try to solve 15 equations by hand. Okay? One equation in each line. It's too much work. You're going to get burned out. Only computers do this type of thing. Okay, so because of that, I'm not going to give you a circuit that has 10 loops and 7 nodes. I'm not going to do that to you. Okay? I'm going to do maybe a circuit just like this one you saw. You know, 3 loops and 2 nodes. Maybe I'll go for 4 loops, you know, and 4 nodes. But now then it starts to become too work intensive, and you won't be able to solve that by hand. You have to get a computer to help you solve that. So in real life, that's what we end up doing. Okay? Multiple nodes and multiple loops. So let's try to solve this problem. Here you go. Did you get the idea? What time is that? 5:37. That's good. 15 equations. That's a lot, right? 15 equations. Right? That just to write the 15 equations, takes a long time for you to do that. Okay. I once had to solve a problem with 10 equations for a client of mine, a student client of mine. I told him, look, you cannot do that by hand. You have to do that with an algebraic manipulator, at least with an algebraic manipulator. Okay? Those crazy professors that are at university, they give you those humongous problems for you to solve. And they tell you that you cannot use a computer. Oh, yeah, you cannot use a computer. You want me what? Spend the rest of my life solving this system of 10 equations? You're crazy. That's when you discover if the professor is reasonable or not. Okay? It's not just difficult, theoretically speaking, solving the problem. It's a matter of too much work to solve. Okay? So let's go ahead and solve this system of equations. The system of equations here is going to be three equations, three independent equations, and I'm going to identify each equation from the drawing that you have here. Here you go. The first one, I'm highlighting loop number 1. Okay? So I chose the loop to go in a clockwise direction. This current I1 is going from the left to the right. This current I2 is gonna go downwards. Okay? And I'm going to start from this point to this point. We are going from positive potential to negative potential. So we lose electric potential. Let's go there. Solution. Minus V2. Okay. What else? What's the next step? We are going to go through this resistor. But note, see, that we are going against the flow of the current. I set up the current to go in this direction, and I'm going against the flow of the current. So instead of losing electric potential across this resistor, I'm going to gain electrical potential because I'm going against the flow of the current, okay? So I can write like that, plus VR1. And then we go, against this guy here. We're going to lose potential energy minus V1. And we have one more resistor. Remember that the current is going upwards. Let's see if I can get that illustration for you. Yep, right in here. Current is going upwards. Right? Lose electric potential. I'm going to lose electric potential too because I'm crossing a resistor and the current is going in the same direction that I'm moving the loop. It's going to be minus VR2. Okay, I got it right. Until we get to the other side of the battery, and we have my first equation. Okay, so here you go. Next one is this loop here. Loop number 2, right? Well, I'm going to go from the negative to the positive terminal. I'm going to gain electric potential. And I'm going to put, here you go, loop number 1. Loop 1. And then group number 2. Loop number 2. Loop number 2. I'm going to gain electric potential. Okay, I'm gonna go through the resistor in the direction of the current flow. So it's gonna be minus V1. Now I'm gonna go through this resistor number 3 in the direction of the current flow. So we're gonna lose electric potential through the third resistor, right? And we have only 3 terms to this second equation, and then we go back to the negative side of the battery. Second equation. We can do the third one, and you're going to find out that this third equation is going to be a linear combination of the other two. Let's do that together, just for practice purpose. Okay, so here you go. Let's start here at this point in the positive plate of the power supply. We're going to lose electric potential. Here you go, loop number 3. We're going to lose electric potential minus, yep. We're going to go through resistor number 3. going through resistor number 3 is a negative proposition, right? You lose electric potential because you're flowing in the same direction as the current. You're going to go through resistor number 2, which is going to be a negative contribution, and we go back to the initial spot. Those three equations here. Okay, like I said, among those three equations, we have only two that are linear independent. How can I prove that to you? Is there a way to prove that to you? How do we prove that those, among those three equations, there is one that is linearly dependent? There's a way to find that out. How do you do that? Huh? Okay, here you go. I'm gonna sum loop 3 with loop, no, sum now, I'm gonna subtract with the negative of loop 2, okay? The negative of loop 2, okay? Let's see what happens. If I obtain loop 1, that's because, we have only two linearly independent equations. What do we get if we do that? Here you go. Sum loop 3 with the negative of loop 1. Here you go. Loop 3 with the negative of loop 2. Negative. Okay, here you go. Let's see what we get. I'm proving to you that, here you go, this V1 here is going to survive, right? What about this VR3 here? See, negative is positive, and you have another VR3 here. See that? Okay. So let's see what we get. We get something like that. And now, oops, here you go. Did I do it right? Oh, I didn't eliminate VR3, huh? Yeah, I didn't eliminate VR3. Let's eliminate that. Okay, this VR3 eliminates this other one. Okay? And then what we get? We got minus V2, and we have minus V2 here. Minus V2 here. Okay? Bold face, bold face. We have plus VR1 here, bold face, and we have plus VR1 here as well. We have minus V1 here, and we have minus V1 here as well. And you have minus VR2 here. You have minus VR2 here as well. So I prove to you that one of the equations is linearly dependent of the other two. So this equation here is linearly dependent on the other two, or vice versa, right? You could also say that this one is linearly dependent of the other two, or you could also say that this one is linearly dependent of the other two. When you are solving a problem like that, what do you want to do? You discover that there is one of the equations is linear dependent. I suggest that you choose, the equations that are simpler. Instead of choosing this equation here that has 4 terms, choose the equation that has only 3 terms to solve your problem, okay? So choosing loop 2 and loop 3 equations, we have, okay, loop 2 and loop 3. We have that. like that. We have, well, so we got our loop equations. Now we have to look at the, now we'll look at the node equation. Okay, so going back here, just like before, the node equations are going to be, one of the node equations is going to be linear dependent. Here you go, here are my nodes, A and B. Okay, current I1 is flowing towards this node, current I2 is flowing towards this node, and they are combining and becoming current I3. How do you write this equation? We write I1 plus I2 minus I3 equal to 0. Okay? So that's how we do it. I1 plus I2 minus I3 equal to 0. I1 plus I2 minus I3 equal to 0. Here you go. Here are my three equations. I'll put them side by side. Oh, there is more. We have to apply Ohm's law. We have to apply Ohm's law here and here and here. Okay. So let's go. VR1. Here you go, this guy. The current that flows through R1 is I1. See that? VR1 is going to be I1 R1. VR1 is I1 R1. VR3 is going to be what? Let's take a look. VR3 is going to be R3 I3. I3 R3. Here you go. Like that. We do the same here. I3 R3. Oops. And I2 R2. Here you go. Now we have, let's take a look, three equations. Three equations. I'm going to highlight which is known, which is unknown, with three unknowns. And the unknowns are I1, I2, and I3. Okay? So here you go. We know that. We know that. We know that. We know that. And we know that. Okay? In principle, you can solve this equation. In principle, we can solve this system. And how do we do that? Okay, we solve the system. How do we do that? How do we do that? We eliminate the unknowns little by little until we find one of them. Then we walk back to find the other unknowns. That's the technique that we use. Okay? Let us start by eliminating I3. Let's eliminate I3. What does it mean, eliminate I3? Eliminate I3 means write I3 in terms of the other unknowns. Okay? That's what it means. Here you go. I'm going to eliminate I3 right now. That's how we eliminate I3. Write I3 in terms of I2 and I1. Make sense? Right? And then what else we do? We substitute I3 in the other equations, right in here. If I didn't do any mistake, are you following me what I'm doing? Here you go. Here you go. I3 is gonna go here. Okay. I3 is gonna go here. There you go. It's gonna become I1 plus I2. I1 plus I2. I1 plus I2. Okay. Now that I eliminated I3, we do not need the equation of I3 anymore, at least now. Later on, we're going to revisit it when we do the walk back, okay? But to make things simpler for you folks, you know, cutting down the amount of unknowns that we have there that may make you get lost, you know, instead of 3 equations, worry about 2 equations. And later on, you revisit the third equation that we abandoned, okay? So here you go. 3 equations, 3 unknowns. 3 equations become 2. Not only 3 equations become 2, but the unknowns also become 2. And now we have only I1 and I2. Do you see how this technique works? What we are going to do next, eliminate I2. I can eliminate I2 from this equation here. I suggest that you use this one to eliminate I2. So let's do that. Eliminate I2. I'm going to here you go, multiply, and I'm going to apply the negative sign here as well. Here you go. I didn't eliminate I2 yet, but I'm going to eliminate in the next step. Here you go. I'm going to pass I2 R3 to the other side. Almost there. Okay, next step, divide by R3. Okay, cancel, this R3 cancels out. This one, divide R3, here you go. That's what my I2 looks like in terms of I1. What we are going to do now, we are going to find out what I1 is equal to. Go. That's going to be the step that's going to get our problem solved. Here you go. I'll get this I2, replace it right in here. Okay. Gets complicated, right? But that's how it's done. And then I don't need this equation anymore. Becomes just one equation for a single unknown. Our system becomes just one equation for a single unknown. Don't forget, I'm going to revisit this guy here. Don't forget about them. Okay? I'm going to distribute the signs. Oh, don't forget this one too. The negative multiplied by the negative becomes positive. I don't need, oh, we can cancel out the I1. See that? I didn't see I1 here. Okay. Okay, so we can cancel out the I1. So let me cancel out right now. So we simplify it, right? Here you go. R3 is going to cancel out as well. Hey, wait a minute. I gotta put I2 here as well. Yep. Here you go. Okay, so let's see what we can do. Distribute R2. R2. Distribute the negative sign. Distribute the negative sign. Okay, here we go. Hopefully I didn't make a mistake. Keep on checking my work, folks. And do that on your side too. See if you get the same answer that I get. I'm doing that on the go here, on the fly. R3 cancel out is R3. So because I'm doing on the fly, it's possible that, it's a possibility that I can make a mistake, okay? Here you go. The negative sign must distribute. Okay, can I do better than that? Let's see. We're going to distribute the negative sign as well. I prefer, here you go, negative here and positive here. Okay. I will need to separate this one here. Because, okay, here you go. And good. Now I have the I1 terms that I can combine three terms with I1. 1, 2, and 3. Okay, so it looks like it's complicated, huh? Hopefully I didn't make any mistake. Let's finish 6 o'clock already. I'm gonna combine the I1 term. Let me put, there's something wrong here. Okay, there's something wrong. Okay, so I made a mistake somewhere here. I can see right now. I'm doing analysis here. Let's see here. Where did I... Okay, yes, I know what I did wrong. Yeah, I forgot to cancel this R3. Okay? Yeah. Okay, just by doing dimensional analysis, I know that I made a mistake. Just by doing a dimensional analysis. V1 here. Okay, remember, it's V1 R3 divided by R3, right? Oh, wait a minute. Oh man. No, wait a minute. No, no, no. Okay, this one is this one. This one is this one. Yeah, okay, so here is, oh yeah, I forgot to multiply by R2. Okay, is R3, yeah, what we had there was correct. I forgot to multiply by R2. That's the problem. That's what the mistake was. Okay, so here we go. Here you go. That's what it is. Now I'm going to combine all the terms that involves I1. Here you go. 1, 2, 3 terms. They all have our I1. Can I do better? Yeah. Okay, so and I'm gonna put I1 in evidence. Okay, I1, like that. Can I do better than that? Let's see, R3, R2, no, I cannot do better than that. Yeah, we can leave this way, and now we solve it for I1. This guy that's in the left side goes to the right side and change signs. Okay. Okay, whatever is in the left side goes to the right side. And we finally get the result for the I1. Hopefully I didn't make any mistakes. It's looking a little bit complicated, but I don't see where if I did any mistake, I don't see where I did. We need to go for a break. Here you go. Let's see if there is any, yeah, there is some sort of symmetry here, okay? Let me show you. There's some type of symmetry here in this equation. Okay, we have V1 plus V2, we have R1 plus R2, see that? Because of the symmetry, you know, I feel that there's no mistake here. And then V1 R3, R1 R3, see that? R2. Because of the symmetry, I suspect that we got it right. So that's what the first current is. If you want to find the second current, in order to solve the problem, you gotta find I1, I2, I3, right? Okay, we got I1. What do we do to solve the problem? Plug I1 here and here. You get I2. Now you have I1 and I2. What do? You find I3 by plugging I1 and I2 here, and you have the problem solved. Okay, so it's 6:04 right now. Any questions about that? I'm going to pause here the